is Kirsten McCabe. I am a biochemist by training. I work in the Global Security Program Office.
And my name is Nick Hengartner. I'm the group leader of the Theoretical Biology group at Los Alamos. I've been here almost 20 years, and I want to welcome you all here.
So why are we talking to you about the COVID-19 outbreak? It's because Los Alamos has a rich history in biological sciences. We have a bioscience division that also works very well with the chemistry division, the theoretical division, the engineering division. This is a multi-directorate focus of the lab that started in 1945 with studying radiation health effects.
And from there, we started studying the impact of radiation on the DNA, and we started the Human Genome Project in Los Alamos. We started GenBank, which is now the repository of a lot of the DNA sequences that we're going to see today. And as the years progressed, we moved more from wet lab towards bioinformatics. And a lot of the things you're going to see today that we're doing are now more on the information science side of the biology.
So with that, what we'd like to start out with is a little bit about coronaviruses, about the history of this outbreak, where we are right now, and then slowly move into the work that we're doing at Los Alamos, both here and with our consortium members within DOE. So what are coronaviruses? They're a large group of viruses. They have this envelope protein. They are a single-stranded RNA virus. They have protein spikes that you see in the graph, which kind of gives it its name of the coronavirus, the crown. There's about 7. Most of those form the common cold. They have generally mild disease effects, but some are more severe, such as the SARS outbreak that was in China in 2003, the MERS outbreak in Saudi Arabia in 2012, and now the China outbreak from 2019. It's gone through a couple different names. Right now, it's the SARS-CoV-2 that is causing the COVID-19 outbreak. So this is a single-stranded RNA virus that causes the COVID-19 disease. It's called Severe Acute Respiratory Syndrome Coronavirus 2. It originated in Wuhan, China. It's very genetically similar with the bat coronavirus. When we look back in time at the SARS, we know that it had this intermediate reservoir of the civet cat. With MERS, it was the camel. With this coronavirus, the COVID-19 outbreak, we're not quite sure yet what this intermediate reservoir is. It's been postulated that it could have been the snake, the pangolin. Time will tell what this is, but right now we don't have definitive proof. What we do know is that we're seeing, obviously, human-to-human transmission. So how does it compare to other outbreaks that we discussed? The MERS had a 34.4% mortality rate. It had a different binding site that this virus used within the human host that led to a higher mortality rate at that time. The SARS has a mortality rate of 9.6. This is numbers since 2003. Right now, the SARS-CoV-2 ranges 2.3 to 3.2%. This is a number that is uncertain and it's evolving. There's a lot of reasons behind this. We are looking at the testing within countries that vary with the amount of testing that you have available. Are you testing only at risk? Are you randomly testing? All this will play into the factor of what these numbers will eventually come over time. As of today, which is Monday, we have over 760,000 cases worldwide, with over 36,000 deaths. How does that compare to influenza? If you look at the CDC guidelines of the data that they produce since 2010, you have anywhere from 9 to 45 million symptomatic illnesses per this period of time, with 12 to 61,000 deaths. These numbers vary greatly due to the symptomatic issues. A lot of people do not take the tests. They go off the symptoms they have that are diagnosed as flu. Also, annually, the death rate, there's a lot of reasons behind what is reported as the death due to comorbidity issues, issues that they might have underlying health effects that cause the death versus flu.
So, for example, in the coronavirus, we see people dying of a heart attack while they're infected. The same thing happens with flu. Unfortunately, we don't count the deaths from heart attack as being caused by the flu, and so the numbers are small. The other number that I'd like to throw into the mix is 1%. That's the mortality rate, more or less, of the 1918 Spanish flu. That was a large outbreak of a new strain, a little bit like the coronavirus, although I don't want to make too many analogies, but it was in a population that was naive, that is not vaccinated, has no resistance, and that outbreak in 1918 killed 50 million people. One characteristic that it had also was that it came in two waves, a fall wave, a spring wave, and then followed by a fall wave. We don't know if this outbreak is going to have the same pattern, but these are the kind of historical observations that we can bring to bear.
So another thing that people are talking about a lot is the R naught. If you look at the slide, there's some comparisons for the COVID-19, which ranges about 2 to 2.5. It can go all the way up to 3.4, I think, right now. And this is the number that shows if one person's infected, what is the average number of people that would be infected from that original infected host. If you compare to H1N1 or the SARS or the MERS, you'll see similar in H1N1 all the way to a MERS, which has up to 7.2. So you have more infection per the infected person.
Another way to think about R naught is the doubling time of the outbreak. So instead of asking how many people you infect or an infected person infects, you ask how fast does the epidemic grow. Right now, our estimates are it grows about every 3 to 4 days, which is pretty fast.
What we're seeing is a higher death rate in elderly over 65 and people with immune-compromised conditions. If you go to the CDC website, you'll see a whole listing of what this entails. And time will tell as we get more data what these at-risk populations are. But you can see certain countries, if you look at, and as well as states and counties, we have different age demographic and different comorbidity demographics. And some of these are all taken into account to look at who we need to protect, why we're putting these mitigation strategies into effect. So the spread of coronavirus knows no boundary. As you can see from these graphs, we had the spread starting in China and then going globally. What I want to bring forth here is the fact that there are a lot of outreach efforts that's been going on with the DoD, with the state, with other entities to work with a lot of the countries such as Africa, such as Jordan, other areas where we have been working on bringing the technology to bear in those countries to be able to identify these outbreaks. So setting up genome centers within these countries, networks where we can talk to the scientists and help them with their understanding and the technology, so that in a situation such as this, they have those connections and they have that ability to reach back to the United States and other partners that they've grown to work with within these organizations so that they can identify this outbreak, better understand it within their country.
We think of the coronavirus as a novel virus that's attacking the world. The fact is, it's not really novel, as we already hinted at. It had a reservoir, it probably lived in bats and probably moved through some other animal before hitting the humans. And we can see those emergence of outbreaks throughout the years. A few years ago, we had Ebola coming out. We had MERS and SARS. In fact, we get essentially a new outbreak or a novel virus jumping species almost every other year. So not only does it not have a boundary, but we're constantly seeing the emergence of diseases, which is the reason we're partnering with our colleagues across the globe to have an international network of surveillance. So, Los Alamos National Lab is actively involved and engaged in helping out, understanding, studying, and especially answering important questions about this outbreak. The scientists, at least from a scientific perspective, what we'd like to know is, how does it spread and how fast does it go? Can it infect people without showing symptoms? We have talked about the asymptomatic or maybe subclinical infections. How deadly is the virus? We already hinted at we don't really know. We can count the dead, but we have a hard time getting the denominator because we are not quite sure if we capture everybody who is sick. Can we engineer a drug? How can we treat it? How is it different from other coronaviruses? What makes this one so special? Why is this particular outbreak moving on so fast and possibly is killing individuals, apparently older individuals and men? That's what the data says. I'm at risk. Sorry, Kirsten. You're fine. And also, what's the cost and the benefit of implementing different mitigation strategies? In the long term, one of the questions that we will want to know is, will this virus become endemic? That is, will it become a recurrent strain that's going to infect us year after year after year and just join the whole cohort of other flu-like illnesses? But for that, we want to ask ourselves the question, can the virus reinfect us? And maybe how fast does it mutate? Because if it mutates really fast, then the immunity that we may have acquired disappears within a year. So these are the kind of questions that we want to answer. And what decision makers need and what we hope to provide is science and data. And we want to support the facts. So we're not decision makers, but we provide what is needed for decision makers to be informed.
So LANO has impacts throughout biodefense. And we've been working in this area, as you saw from our first slide, for a very long time. What we're doing right now is working on how do we take that base knowledge that we have, our core disciplines, and work on this and leverage it for the COVID-19 outbreak. So we're going to talk to you a bit today about some of the topics that we have listed here. We will not be able to cover everything the lab is doing right now. The lab is making a fantastic effort in a combined way to work on this. We're just going to highlight some areas. And at the end of the talk, we're going to give you points of contact if you want to get in touch with them for these areas. We'll start with detection and diagnostics, some of the ways that we're optimizing assays, looking at phylogenetic tree analysis, moving into epidemiological modeling, something that we've been doing very heavily for the last month, with disease prediction and forecasting. All this for decision support. How do we get the data that helps work on decision support, the data collection, the integration, the SME reach back to answer questions that we have this knowledge in. And then ending on medical countermeasures, vaccine optimization, which is a strong point for the lab, small molecule discovery, and toxicity testing. So to begin on this with detection and modeling, one thing to know is what has happened in the past in historical outbreaks. We have a database that looks at outbreaks over time for different scenarios. What is endemic in areas? When something occurs, we can look at these tools and see if it's matching what we've seen historically. If it's not matching, it alerts us that something might be different. It also shows us what happened in the past that people used for mitigative actions. Did they work well? Or can we learn from them at what did work well and what did not work so well? For assay detection, we've had a long history in optimizing assays. As bacteria evolves over time, as we get more information on genomes, that changes our assay signatures. They kind of erode over time. We need to keep pace with that and deliver assays that will be functional for COVID-19 or outbreaks of the future. For diagnostics, we're trying to leverage ways that we understand the host innate immune system. How can we triage what's going on in the field? How can we understand if you have a bacterial or a viral infection? So these are all work that we do at the lab that we're trying to leverage for this COVID-19 outbreak. The DOE has laboratory testing capabilities. We are leading a DOE-wide laboratory working group on testing. We have participated in assessments for the lab capabilities from everywhere from near-term, right now, to long-term testing requirements, both for public health and for our enterprise. There's been 5 R&D tasks that have been awarded by DOE, and LANO's participating in 3 of those right now. We're coordinating requirements for regional testing with Sandia. We already have CLIA registered number for a lab housed at Los Alamos, and we're working very closely with the New Mexico Department of Health. We're working both on the testing side, but also on the modeling side. For modeling, we're looking at the spread of disease. We look at it globally, all the way down to the county level. So in New Mexico, we're looking at county level. We're looking at how is the disease spreading. What are the forecasts forward for when we will see a peak in cases? How many people might be hospitalized? How many in the ICU? How many might need ventilators? Both from no intervention all the way through to high intervention. There is a site at Los Alamos. It's the Gateway, Biosurveillance Gateway, a site at Los Alamos that you can look up, where we'll be housing some of this data, but it's also a place where you can go and see some of the areas that we're working at, and you can also look at who to contact for some of these efforts, put in questions, and we will triage those and try and link you up to the scientists that are working in this area.
One way to think about an epidemic model is a chain reaction. I have one infected person that infects 2 others, that infects 4, and so forth. Now, contrary to a bomb, which we know quite a bit about, we burn out of fuel eventually. That's when we achieve, or that's when the epidemic stops. We can try to slow it down by adding impurities, i.e. vaccination or isolation. Those people are then quarantined and are not involved. So because we have those kind of physical models that are reasonably realistic and we can model them at low level of geographic aggregation, it allows us to actually validate the data. One of the things that comes out is that we believe we don't see everybody who is sick at this time. There may be many reasons for that, but that is something that our model is able to tell us. It's also able to tell us if the mitigation or the strategies that we're implementing are working, because we can compare what the models predict with the actual data that we are collecting. Part of the modeling also uses the basic law of biology. The basic law of biology is genomics or evolution. If there's one law in biology, things evolve. And by looking at how those viruses evolve and putting them in context of related organisms, and that's what this tree here shows us, we can make several conclusions. For example, we know now that the COVID-19, that virus is different from the SARS. It's not the same. It's related, but it's not the same. The other thing we can see is how fast or slow it evolves. This particular virus evolves relatively slowly, which is good news, and I'll get to that in a minute. And it also is able to show us close neighbors or related viruses. And some of the related viruses were in bats and some in pangolins. And so this is why we make the statement that, well, that virus is closely related to bat. Maybe it came from there. But this is the kind of analogy what we do. When we look at sequence similarity and compare it, one thing that we see is that this particular virus not only made use of point mutation, but it also rearranges its genome a little bit. And looking at the patterns on how it has been rearranged and point mutations, we're very confident to say that this follows what we would expect from a naturally emerging and evolving organism. Going a little bit further, we also can not only look at the tree, but also look at where geographically the strains have been sampled. What we see is that the strain is evolving slower than it moves across. We get something that people call the emergence of strains. Those strains, to be honest, are not that different from one another. They have a few mutations different, so it's kind of a stretch in my personal opinion to call them strains, but we can see already some geographic differences emerging from this particular outbreak. If we look at how infective these are or how deadly, we see no differences. So although biologists will say, yes, we see some differences in the evolution, in this particular case, we haven't seen anything affecting some of the consequences we fear about. The other thing that we can do is go one step further. So the DNA gives me the book, and I can read that book and make protein out of them. And one of the interesting proteins of the coronavirus, you might guess, is the crown. It's those spikes. And the reason those spikes matter is because it is those spikes that attach themselves to the surface of a cell, and then somehow it's able to inject the RNA into the cell, and that's how the infection happens. For that to happen, this attaching to the cell membrane, there are two receptors. There's this little thing here called the ACE2, ACE2, and the salic acid, which is here. These two are location where the spike will get in contact, attach itself to the cell membrane, and do something. Now, it turns out that the fact that this virus has two ways to attach itself to the membrane is actually not common. And one of these receptors is in the upper lung, and the other one is in the lower lung. And so this may also give a hint on how this disease can progress, that it's a respiratory disease, it gets in the top of the lung, but then it's able to go down further. And so this is good information that tells us what to do. So now that we know it binds with those receptors, this provides us an opportunity to say, well, are there any therapeutics that could mitigate or disrupt this kind of behavior? And so this already tells us what kind of molecules or drugs we should be looking for, just looking at the structure of the molecule.
So now when we have these drug candidates, it would be fantastic to be able to test them rapidly in a human-based system, something that's clinically relevant to the human. Right now, most tests go through animal testing. So what we're trying to do at Los Alamos is bridge that gap and have a human organoid platform that would better mimic what would happen within the human host. So this is our project with Athena, where we have human heart, lung, and liver. We would like to work into the future with understanding how to build immune system into this platform. But for right now, these are systems that would be able to screen some of the drug candidates that are out there.
As you probably know, people are feverishly trying to develop a vaccine, and people already have designed vaccines that are in testing phase. But at Los Alamos, we also want to look into the future. And one of the risks that we've recognized with this coronavirus is that there is actually this immense pool of other diseases out there, other coronaviruses, hiding in bats and pangolins and snakes and whatnot. And it would be nice if we could come up with a strategy to protect us, not against this particular strain, but maybe next year's jump. And using some of the strategies that were developed in designing an HIV vaccine, and there, this problem with HIV, it mutates extremely fast, so you have a broad diversity. In our case here, we argued it doesn't mutate that fast, but we have a broad diversity because there's a lot of them out there. And so if we can use similar strategy, we can start thinking about designing a vaccine that will protect us of future infections and outbreaks, somehow nip this one in the bud at the get-go.
On the manufacturing side of the house, we've been working in a DOE-wide working group, participating in assessments how the labs can support ventilators, masks, face shield, consumable parts for lab testing. Right now, we're in the deep dive phase, trying to figure out how do we help, what is the best way that we can work with our commercial sectors on some of the things that you see here. Test platforms to making valves, to making filters. We are working through that right now, and there is a working group on this. In conclusion, public security, public health is a national security issue. We don't know everything, but we're leveraging our international networks, our community tools, to tell us what needs to be done and to advise how to beat this outbreak. We do have a COVID-19 information page on the LANL home site, and we have a COVID-19 special office that's organizing all the great science that you see here and working on bringing everybody's skill sets to bear on this challenge. This is the point of contacts for the different groups that you can find in this special office. It's led by Pat Fitch. We have modeling support for response, laboratory testing, manufacturing, application of AI and machine learning, medical countermeasures, and high-performance computing. So these are some of the point of contacts that you'll be able to reach out to if you have specific questions within this area. These are areas that we have working groups already built, trying to harness the lab's capabilities both within our community and with our DOE consortiums. If there's media inquiries that come your way, we ask that you coordinate with the LANL Communications and Public Affairs Group. They will coordinate responses back to the media through the DOE and NNSA Public Affairs Group.
And in closing, I want to remind you that the best way to stop this pandemic is social isolation, hand washing, and be safe. So with that, I'd like to have a round of applause for everybody here.